All right. Hi, everybody. How are you guys doing? So the plan here for today, my voice is starting to go on me a little bit. I don't know how long we're going to go. I'm going to try to finish 15:1 at least, and then see how my voice is feeling, because it just may not be a lot in the cards for me today. But that's the plan. All right. So I want to just kind of touch on or review a couple of topics from 15:1 before we get started, and finish up with 15:1. So we had last time talked about exponential functions, and we said that there was kind of two different ways that we could represent them. Right? And then amongst our exponential functions in either representation, we can have growth or decay, right? So I just want to review here and do an example or two for identifying whether something is exponential growth or decay. So if for growth, we can have two situations: when a is greater than 0 and when a is less than 0. When a is greater than 0, we need b greater than 1. And when a is less than 0, we need b between 0 and 1. So, for example, y equals 2 times 3 to the x is growth, and y equals negative 2 times 1/3 to the x is growth. Everybody's okay with that? Now, decay is going to be the opposite. So when a is positive, then I need b between 0 and 1. And when a is negative, I need b greater than 1. So y equals 2 times 1/3 to the x is an example of decay, and y equals negative 2 times 3 to the x would be an example of decay. We feel so far so good? So if we're in the other form with the e in it, if a is positive, then for growth, k needs to be positive. And if a is negative, k needs to be negative. So y equals 2 times e to the 3x, and y equals negative 2 times e to the negative 3x are both examples of growth. And then for decay, if a is positive, then k needs to be negative. Or if a is negative, then k needs to be positive. So y equals 2 times e to the negative 3x, and y equals negative 2 times e to the positive 3x are both examples of decays. Everybody's okay with this? If I were to ask on a homework quiz to identify if something is growth or decay, or what the criteria is, to determine if something is growth or decay, I would expect you to be able to repeat at least portions of this, right? I might tell you, like, you have this equation and like this value of a. Tell me what it would be for growth or decay or whatever. Does everybody feel okay? So just kind of, you just got to remember what this stuff looks like. The other type of problem that we did yesterday is writing the exponential equation. We did this two ways. We had like a table of points. Such as this. If we have a table of points, and one of the points, the x-coordinate is 0, this is no problemo. So the goal is to write our f of x equals a times b to the x equation. To do that, we're just going to plug in our x and y coordinates into x and f of x. Because we have that 0, I know b to the 0 is 1. So I'm left with a equals 1 in my equation. Using that, I can then pick another point from my table, say 1, 2. Again, I'm still trying to write this equation, but now I'm going to put 2 in for f of x. My answer for a in for a, and my value for x in for x, and solve. So putting those two together, my equation is f of x equals 1 times 2 to the x, or just 2 to the x. Since 1 times anything is still just 1, right? Or still itself is not 1. Come on, Mr. Kulik. That's very wrong. So far, so good. We remember kind of doing this stuff last time. Okay, I just wanted to kind of rehash since there was a rather long weekend in between. What I want to do next is just do some story problems examples. Okay. So this example says, given that the population of a certain city in 1990 is 782,248 people, and the same population of the city in 2000 is 895,193 people, assuming that the population growth is exponential, in what year will the population reach 1 million people? So when I read a question like this is going to be a two-step equation or two-step problem. Step one, I got to write my equation, and then step two is I'm going to need to solve it. Everybody's okay with that? So to write my equation, I need to identify my two variables. I'm going to use T for time and P for population. Everybody's okay there? So doing that, I have 2 points then. $1990, 782,248, and then 2000, 895,193. Now, this is fine the way I've written this, but notice that neither of my x coordinates is 0, right? Which means I'd have to do that other way of writing my equation. That's a lot harder. So I'm going to do this. Instead of calling T just time, I'm going to make T the years after 1990. I'm going to leave P still just population. But if T is now the years after 1990, the x-coordinate of 1990 now is just 0, right? Oh, Mr. Kulik. This is a clever idea. 2000 then would become, how many years after 1990 is 2000? 10. And I like this because what is that going to give me basically for free? Is that's my A. Sound good? So P, I'm going to write P is equal to A times B to the T. I have a T and a P and an A. So all I need to do is solve for that B. So if I want to solve this equation for B, what should I do first? Anybody got an idea?
Get it by itself.
Great. Get it by itself. That's what I would want to do. How am I going to do that, though? What mathematical operation am I going to do? Perfect. So divide both sides by 782,000 and change. Now, I could type that into my calculator to get a decimal, but I'm not going to bother with it because it's all going to go into my calculator later anyway. So I'm just going to write it as a fraction and save myself the hassle. It's just going to not open. Sweet. Okay, well, it's going to be a pain for me. Now, how am I going to get rid of that power of 10 attached to the b? How would I get rid of that? Right, I got to get rid of this guy right here. What's going to cancel out an exponent? You should all have an answer to this. It is all within your scope of knowledge. Not a square root, but a different kind of root, right? Yeah. What kind of root? Not a cube root. A 10th root. That is correct. Now, we do need to be a little bit careful, though, because this is an even root. What do we also need to create when we do this to both sides? Gives you a plus or minus. But remember, what do we know about exponential equations and the value for b? The value for b must be positive. So we can just discard the minus from the plus or minus. And now I can just compute this decimal onto my calculator, but I'm not actually going to compute the decimal. I'm going to use the whole number here. I wish this stupid calculator would open. All right, let's try doing it this way. It's being really stubborn. Open. For the love of Pete. Why are we being so stubborn? All right. That's not what I meant to do. Fine, whatever. Yeah. Yeah. Hold on a second here, guys. This is not going to work here. Let's try one more time. That makes total sense. All right. Well, we can't show you on this calculator because apparently everything is just on revolt here today, technology-wise, so that's fine. So the end of our step one, then, we have our equation. P is equal to 782,248 times the 10th root of 895,193 over 248 to the t. Everybody's okay with this is the end of step one? Yeah, Bella? Yeah, so this number here is called the index, and that will match whatever exponent you're trying to cancel out. So if you had like b to the 7th, you'd use a 7th root, or if you had b to the 19th, you'd use a 19th root. Sure. So for step 2 then, it asks us to find the time when the population is going to be 1 million. So we're going to solve this equation, right? We do not have the tools to do this algebraically. What are we going to do? We're going to graph this on our calculator and find the intersection. So into y1, we're going to type the left-hand side of our equation. And into y2, we're going to type the left-hand side of our equation. Then we're going to set our window. And the 4 components in the window we need to worry about are our x min and max and our y min or max. Remember that the x, the independent variable, is the years since 1990. And our population is, or y is population, right? So let's think about our x min. Since it's the years since 1990, a good x min should be 0, right? That's the first point I know about. Let's think about our x max now, because we're going to have to make a little bit of a guess. I know when t is 10, we're just short of 900,000. So in 10 years, we grew about 100,000 people. I would expect in another 10 years, we'd probably grow similar, about another 100,000 people. So I'd expect by year 25 or 30 to have topped 1 million pretty easily, right? So I'm going to make my guess there for an x max of, say, like 30. I'll usually overshoot rather than undershoot because I don't want to have to go back and change things. Does everybody feel okay there? Now, our y's are about population. So the smallest my population ever is this 782,000, right? So I'm just going to round down because I don't like, like goofy big numbers like that. I'm just going to call that 750,000. Just a little less than whatever that minimum point is. Now the x max has to be bigger than 1 million because I need to see the intersection. So I'll just pick like 1.25 million. It doesn't really matter. It just needs to be bigger than my 1 million that I'm trying to find. So if you have your calculator with you, I invite you to take it out and try typing this stuff in and finding the intersection, seeing if you can get it. I would love to show it to you on the screen, but my calculator or my computer's in revolt. I guess I should say, do you guys know how to get a 10th root onto your calculator? Okay. So you'll type in the number 10. Then you'll pick the math button and you'll pick command 5. And you should have a 10th root then in there after that. At least it's command 5 on my calculator. On the calculator, it looks like that. Yes. Did you guys have any luck getting it into your calculator and finding the intersection? I don't know why we're being so stubborn about this. Let's see. Ah, there we go. For whatever reason, it thought it was running and then not. And after some end tasking, I got it. All right, so into my calculator, I typed 782,248 times parenthesis the 10th root of, so I did the number 10, math, command 5. So you see how the 10 is now like a 10th root? And then I'll do that fraction command. So I have 895, 193 over that 782, 248. Then I'll close my parenthesis and raise that to the power x. And then 1 million in the next thing. Set my windows. We said 0 to 30 would be a good guess. And then 750,000. Then 1.25 million. So if I hit graph, here we go. Bella, will you grab that door and just pull it shut? This is like the second or third time a big herd of people has come by, and I'm too hoarse to feel like yelling over them. So there's my intersection. To find that, I just do second and trace. Pick the intersect command. There's just two lines and one intersection, so I'm just going to press enter 3 times. And there's my 8.2-ish for my answer. Everybody okay there? Now, let's read the question here carefully, though. It says, in which year or in what year will the population reach 18 or 1 million people? So, did I answer the question? Not exactly, right? What should I say? We would say in the year, what? 2008, right? Everybody's okay? What if the question had instead said, at the beginning of what year will the population reach 1 million people? How would I have answered it then? Should I answer 2008 or 2009? $2009, because if I round down, am I going to be more than 1 million or less than 1 million? Less. So just got to be careful on the wording, on how you do the rounding. Is everybody okay there? So depending on what they're actually asking for, could be during the year 2008, or could be at the start of 2009. Does everybody feel okay there? All right. So what will the population be for this same thing in like 100 years? Well, all I would do then is just plug 100 in for t, right? So if I do that, the population for the city is now 3 million people. So it went from 782,000 to 3 million people. Not sure I buy that. What would the population be in, say, 200 years? $11 million people in change. This is not seeming so plausible here, that this mid-sized city all of a sudden becomes New York City size, and like, aren't there limiting factors how big your city can be? Like there's only so much land to build on. There's only so many spots for houses and apartments and stuff. Like how are they getting to like 11 million people here, or almost 12 million people? This brings into focus, ideally, an issue with using an exponential function to model a population. Is a population going to continue to grow forever? Probably not, right? It's gonna reach some kind of limits on how big that population can get based on the resources that are available, whether it's space or food or, like disease, or, like the denser your population gets, the more problem diseases become, and other stuff to limit population growth, right? So an exponential model might not be the best fit for describing something like population. Can we think of another, another thing in the real world that we might want to measure that probably has like an upper limit to it, like population, that could grow very fast for a little while, but eventually it's going to like slow down and stop growing? The economy, sure, that's reasonable. So like the mining of natural resources, like the availability, sure, in the beginning you can get a lot out, but eventually that thing gets scarcer and scarcer. You have to work harder and harder to get something out. How about human performance? Like if you're, weight training or something, in the beginning you make crazy fast gains, but eventually it slows down and you start having to work really, really hard for those next marginal gains, right? Does that sound familiar, those of you that are involved in athletics? Yeah, so what we want is ideally a model or a type of function that will do a better job of describing that kind of behavior. So the idea here is that we'll have something called a logistic function. So this is our two different versions of our logistic function. Yes. Sure. So our logistic function is just something of the form c over 1 plus a times b to the x. Or instead of a times b to the x, you could have a times e to the kx. Either way is fine. So those constants a, b, c, and k, we're going to say are positive. So we're always going to assume that a, b, c, and k are positive. When that b is less than 1, so between 0 and 1, we call that logistic growth. And when it's bigger than 1, it's decay. Similarly, if the k is positive, it's going to be growth. If the k is negative, then it's going to be decay. The neat part about this, though, is that this is going to be a function that has two horizontal asymptotes. One of them is going to be at y equals 0, and the other will be at y equals c. That y equals c we'll call the limit to growth. And if we look at the graph of a logistic function, you have one horizontal asymptote here at y equals 0, another one here at y equals c, and in the middle you have like this kind of S-shaped curve. So notice in the beginning, we're growing very fast, like an exponential looking curve, like an exponential growth. But at the end, we're growing more slowly. It's kind of looking like the exponential decay at some point. It switches down and it starts like that growth peters out. Ella? Sure. Does everybody kind of see that? So it grows really fast in the beginning, but then like the growth really tails off towards the end, which is what we see a lot of times in real life with, you know, population or the economy or natural resource production or human performance. So let's take a look at some examples here. So it says graph the following functions on your calculator, find the y-intercepts, and find the equations for the horizontal asymptotes. Well, we'll graph these things, but we don't need to do that to find what it's asking for. How do I find a y-intercept? I don't set the denominator equal to 0. I want to plug 0 in for x, right? I just do f of 0. So that's what I get, right? What's 0.6 to the 0?
0.
Nope. Nope. Anything other than 0 to the 0 power is 1. So that just kind of like cancels out, right? So in the denominator, I just have 1 plus 3. So my y-intercept is the point 0, 2.5. So far, so good. So I recognize that this is a logistic function because of the form that it's written in. So I always have y equals 0. And my other one is going to be y equals c. The c is just the numerator. So y equals 10 would be my other horizontal. Let's type this in and graph it on our calculator and take a look at the picture. So again, I'm going to use that fraction command on my calculator. And then we'll graph this, say, from like negative 100 to positive 100. And my y-min should be 0, the horizontal, and my x-min should be 10, the other horizontal. And I guess most of my action happened a lot closer in, so let's just do that, get a better picture. That's better, right? Okay, try to do B. Find the y-intercept and the horizontal asymptotes for me for B. Yes. So when you plug in 0 for x, you'd have e to the 0, which is 1. So the denominator would turn into 1 plus 4. So that will give us the y-intercept, right? Just 31 over 4. Or 0 comma 31 over 4. We probably should write it that way. Who can tell me what the y or the horizontal asymptotes are going to be? One of them should be easy. One of them should be easy. 0, y equals 0. And the other one should be y equals c. The c is 31. Does that feel okay? Pretty easy, right? No big deal. You just have to know what you're looking at. All right. One more example, and that's probably all my voice has in me today. All right, this says the population of a city can be modeled using the logistic growth function, P of t equals yada, 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 where P is the population in the city T years after 1950. Notice here they use that same trick that we did on the previous problem when we wrote our model. Rather than having to go 1990 and have like huge numbers for x in there, we just simplified. At the beginning of what year will the city have 1 million people? Well, this is now no longer a two-step problem. Why is there no step 1? Because the equation is given to us. So we'll still do things the same way. We just need to solve 1 million equal to P of t. Again, do we know how to do this algebraically? We do not. How are we going to do it? Graph it in the calculator and find the intersection. So I'll type in P of t into y1, or you could type a million into y1. It doesn't really matter. 1, 4, 2, 5, 3, 9, 7. 1 plus 2, 1.783 times e to the negative 0.04982x. Is everybody okay there? Okay. So for a window, I'm going to start at 0 for 1950. I don't know how long it's going to take, but given the life of a city, I would think no more than 200 years, right? I don't know how big this city is in 1950. I guess I could figure it out by just computing the y-intercept, but I don't probably need to do that. I can probably just go to 200 and be fine. Now the y-min will be 0, and the y-max will be the other horizontal asymptote, which is 1,425,000, but I'm not going to type in all those numbers. I'm just going to call it like 1.5 million. Is that? Yeah, that's the right number of zeros. Okay, and I'll hit graph. So here's my population curve coming in. There's my 1 million line. We'll just find the intersection. Second trace, intersect, enter, enter, enter. And we get T is about 79.001. But look at the question. I'm going to take that intersection and convert it to the answer to the question. Am I going to be rounding that 79 up to 80 or down to 79? Up to 80. And then we'll add that to 1950. So our answer is the year 2030. Everybody feel good with that? All right. This is where we're stopping because I'm out of voice. This just finished up 15-1. So again, if you started that homework and you ran into the story problems and were like, what do I do with this? We've done enough example, I think, that you can probably finish those guys up. And then the next section is more exponential story problem situations that we'll look at. But that's for next time. Those of you that are going on Kairos, we're going to just do 15-2 and then 15-3 on Wednesday and Friday. So you just have some homework lessons to pick up. We didn't add anything to the homework today, so it's still the set for Friday. It's just 1 through 16 now. We'll add to it when we do section 5-2 on Wednesday. And then the 15-3 homework wouldn't be due till the following Sunday. So you'll have, if you're caught up on your 1 through 16 today, you only have one set of homework to worry about getting in when you get back from Kairos. And it's, I don't think too bad. It's just basically story problems. Okie dokie artichokes. Okay. Once you guys take the remaining 30 or 40 minutes here of class and try to get a jump on the homeworks here. Sound good? Okay. That's all the talking I have in me.